This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. We'll be delving into a research paper focusing on improving the reliability and interpretability of computer vision systems, particularly in critical applications like autonomous vehicles. The paper introduces a framework called CAIR. What are the core challenges addressed by this framework?
The core challenges revolve around the limitations of current testing and evaluation, T&E, methods for computer vision CV systems in safety-critical domains. These systems, often trained on massive datasets, are prone to failures in rare or unforeseen scenarios. CAIRO aims to address the lack of meaningful mapping between the perception of an autonomous vehicle, AV, and a human's perception, and the oversight of human factors like fairness and trustworthiness in existing CV model evaluations.
The paper mentions the limitations of formal verification techniques in CV, unlike in chip design. Can you elaborate on why this is the case and how CAIRO attempts to bridge this gap?
Formal verification is well established in chip design due to the relatively closed and well-defined nature of the system. CV applications, however, are open-ended, trained on vast datasets with billions of parameters to learn a few hundred labels. Fine-tuning practices are common, but lack standardized testing procedures. CAIR attempts to bridge this gap by introducing a human-in-the-loop (HITL) approach, using ontology-based knowledge graphs to formalize failure cases, critical phenomena or CPs, and enable systematic validation.
The paper highlights a hybrid open-world assumption, OI, and closed-world assumption, CLUA, approach. Explain the rationale behind this hybrid approach and how it contributes to human-machine teaming.
While large AI models benefit from OA's flexibility to learn new concepts, the finite nature of critical failure modes necessitates a CWA for effective rule formulation. The hybrid approach combines the strengths of both. OA allows for flexibility in representing the diverse real-world scenarios, while CWA enables the precise definition and validation of CP rules. This allows for human experts to leverage their domain knowledge within a structured framework, facilitating human-machine collaboration.
The paper describes the use of knowledge graphs, KGs, and ontologies. How do these contribute to the interpretability and scalability of the CAIR framework?
KGs provide a structured representation of the knowledge extracted from the input data, making the reasoning process transparent and understandable. Ontologies define a common vocabulary and relationships between concepts, ensuring consistency and facilitating knowledge sharing. This structured approach enhances interpretability by allowing for tracing the reasoning steps leading to the identification of CPs. The modularity of KGs also contributes to scalability, allowing for the framework to be adapted to different use cases and datasets.
The methodology involves several steps, including detection, segmentation, feature extraction, ontology graph construction, formalization, reasoning, and HITL validation. Can you elaborate on the role of HITL in this pipeline?
HITL is crucial throughout the pipeline. Humans validate segmentation outputs, refine formalization rules based on domain expertise, and oversee the reasoning process to resolve ambiguities. This collaborative approach ensures that the system's outputs are accurate, reliable, and aligned with human understanding of criticality. The HITL component is particularly important in handling complex or ambiguous scenarios where automated systems might struggle.
The experiments involve using 2 datasets and various adversarial attacks. What were the key findings from these experiments regarding CAIRO's ability to detect and analyze CPs?
The experiments demonstrated CAIRO's ability to identify CPs in diverse scenarios, including those involving behavioral unpredictability, dynamic object properties, and adversarial attacks. The use of patch attacks and noise-based attacks showed that CAIRO could still detect object-level issues even when the detection model was fooled. The results highlight the robustness of the framework in handling real-world complexities and its potential for improving the reliability and safety of AV systems.
The paper mentions the use of different object detection models, faster RCNN, grounding dyno, CLIP, and a segment anything model, SAM. What was the rationale behind using multiple models, and how did they complement each other?
The use of multiple models was strategic to overcome the limitations of individual models. Faster RCNN and grounding dyno provide initial object detection, but their performance can be limited by predefined classes and reliance on text prompts. SAM refines bounding boxes, and CLIP helps classify regions, filling gaps left by the other models. This ensemble approach ensures more comprehensive object detection and classification, leading to a more robust ontology graph construction.
The paper discusses the use of SWRL rules for formalizing CPs. Can you elaborate on the advantages of using SWRL in this context?
SWRL, the semantic web rule language, allows for the creation of complex rules that combine multiple properties and relationships to define CPs. This expressiveness is crucial for capturing the nuanced nature of critical phenomena in real-world scenarios. SWRL's integration with ontologies enables the formalization of CPs in a structured and consistent manner, facilitating reasoning and knowledge sharing.
The paper mentions the use of description logic, DL, and reasoners like Pellet and Hermit. What role do these play in the Cairo framework?
DL provides a formal framework for representing knowledge and reasoning about it. Reasoners like Pellet and Hermit are used to perform inference on the ontology graph, identifying implicit relationships and inconsistencies. This allows for the detection of CPs that might not be directly observable from the raw input data. The reasoners ensure logical consistency and help in uncovering hidden patterns and relationships within the data.
The validator module allows for feature modification to support counterfactual analysis. How does this contribute to understanding the root causes of perception failures?
The validator module enables controlled experimentation by allowing modifications to specific features of the CPs. This allows for investigating what-if scenarios, helping to determine the causal relationships between specific features and the occurrence of CPs. For example, modifying pixel values or segment scales can help isolate the visual attributes or object proportions that contribute to perception failures.
The paper mentions the use of the 6LM architecture. How does this contribute to the consistency and shareability of the generated OWL files?
The six-layer model, 6LM, provides a standardized architecture for representing the operational design domain, ODD, of autonomous vehicles. By leveraging this existing schema, Cairo ensures consistency in the representation of scenarios and CPs. This consistency makes the generated OWL files easily shareable and understandable across different systems and researchers, promoting collaboration and knowledge sharing within the community.
The computational cost is mentioned in Table of the 3. What are the major computational bottlenecks in the Cairo pipeline, and what strategies could be employed to improve efficiency?
The major bottleneck appears to be the CLIP classification process, which takes significantly longer than other steps. Strategies for improvement could include exploring more efficient CLIP implementations or alternative classification methods, optimizing the reasoning process, potentially through parallel processing or more efficient reasoners, could also improve overall efficiency. Furthermore, exploring techniques for reducing the number of features extracted could also contribute to faster processing.
The paper concludes by highlighting future work. What are some of the key directions for future research and development of the Cairo framework?
Future work could focus on expanding the scope of Cairo to other domains beyond autonomous vehicles, exploring the use of large language models, LLMs, for automated CP rule generation, and developing more sophisticated methods for explaining the reasoning process to non-experts. Improving the efficiency of the pipeline and integrating more advanced reasoning techniques are also important areas for future development. Finally, collaborative efforts in human-centered AI are crucial for ensuring the responsible and ethical development of these systems.
The paper demonstrates the successful application of Cairo in identifying and formalizing critical phenomena in autonomous driving systems. How does this contribute to the broader goal of building safer and more reliable AI systems?
By providing a structured and interpretable framework for analyzing and evaluating the performance of computer vision systems, Cairo directly contributes to building safer and more reliable AI systems. The ability to identify and understand the root causes of perception failures is crucial for improving the robustness and safety of these systems, particularly in critical applications where human lives are at stake. The framework's emphasis on human-in-the-loop validation further ensures that the system's outputs are aligned with human understanding and expectations.
The paper mentions the availability of Cairo artifacts. What kind of resources are available, and how can researchers access and utilize them?
The Cairo Artifact Repository provides access to the code, datasets, and ontology models used in the experiments. This allows researchers to reproduce the results, extend the framework, and adapt it to their specific needs. The availability of these resources promotes transparency and facilitates collaboration within the research community. The repository serves as a valuable resource for researchers interested in developing and improving the reliability and interpretability of AI systems.
The paper highlights the importance of addressing adversarial attacks. How does Cairo's approach differ from traditional methods in handling such attacks?
Traditional methods often focus on improving the robustness of the detection model itself to adversarial attacks. Cairo takes a different approach by focusing on detecting and analyzing the impact of these attacks on the system's perception. Instead of trying to prevent the attacks entirely, Cairo aims to identify the resulting CPs and understand how they affect the system's behavior. This allows for a more comprehensive understanding of the vulnerabilities and potential risks associated with adversarial attacks.
The paper emphasizes the importance of knowledge sharing and community building. How does the ontology-based approach facilitate this?
The use of ontologies and KGs promotes knowledge sharing by providing a standardized and consistent way to represent knowledge about CPs. This allows researchers to easily share and integrate their findings, fostering collaboration and accelerating progress in the field. The modularity of the KG approach also allows for the framework to be easily extended and adapted to different use cases and domains.
The authors mention the potential for using LLMs for automated CP rule generation. What are the potential benefits and challenges of this approach?
Using LLMs offers the potential for automating the creation of CP rules, significantly reducing the manual effort required. However, this approach also presents challenges. Ensuring the accuracy and reliability of the automatically generated rules is crucial, and careful validation and human oversight would still be necessary. The ability of LLMs to handle the nuanced and context-dependent nature of CPs also needs to be carefully evaluated.
The paper discusses the use of various tools, including Pellet, Hermit, and Protege. What are the specific roles of these tools in the Caro pipeline?
Pellet and Hermit are description logic reasoners used for performing inference on the ontology graph, ensuring logical consistency and identifying implicit relationships. Protege is an ontology editor that facilitates the creation, visualization, and management of the ontology. These tools provide essential functionalities for building, reasoning with, and managing the knowledge graph within the Cairo framework.
This has been a comprehensive discussion of the Caro framework. Thank you.